Okay. First of all, let's see. I've got some slides here. Mostly, I want to just start out by saying that probably the best use of me is not for me to like drone on for this like full time slot, and I would really like it to be interactive if we can. I understand there's some microphones around. There's apparently one here. Is there another one somewhere? And I am perfectly willing to be interrupted at any time today, including while I'm up here talking. Because I really, if you've got a question, please let me know, and I may handle it in the moment, or I may say, okay, we're going to get that in just a second. Partly, I'm trying to be as helpful as I can. Part of what I'm going to talk about is how GNU Radio got started, and there's a very relatively small number of people that were there at the beginning, and now there's more people. So I want to kind of make sure that we take a look at how it happened, partly because Ralph had asked me, he'd heard me do a similar talk a year ago, and he found it useful. And part of what I'm looking for is, what do I have that I could share that will help us continue GNU Radio for another 20 years, and how all about it, like the community, how do we build it? Where do we go? How do we fund it? Do I have to point this in anywhere? It's on red. Is that the green? Okay. Okay, introduction. Okay, so what do you need to know about me? I think that's the thing is that I founded the GNU Radio project, and I'll talk about how that was, and that was in 2001. And then I worked on it as a full-time endeavor for about 9 years. And what else do you want to know about me? That most recently, my last sort of professional engagement was I was working at Planet Labs, which is like a new space company, and I was designing the high-speed radios that downlink the images. Planet was in the business of, in one sense, a data company or a platform company, and we had 150 small satellites in orbit that covered all the land and coastal areas of the Earth every day at about a 4-meter resolution. And then we had some other satellites that could do like about 50-centimeter resolution. And now we have some in orbit right now that'll do about 30-centimeter resolution. So what's great about those is you can, by some just continuing to tune over time, it's now running at about 1.9 gigabits a second, which is quite an accomplishment out of a 2 watts in a little thing that's 3 liters big. And then we went on to build for the satellites that can do the 30-centimeter resolution. Plus, one we just launched about 2 weeks ago was a spacecraft is called Tanager, and it has got a very fancy hyperspectral instrument in it that was designed by JPL. Got 450 bands. It was primarily designed, or let's say it was primarily funded by people who wanted to keep track of methane emissions, from orbit. You can find leaky pipelines and ships and everything. But in fact, it's a completely general instrument. And, it's very, very snazzy-dazzy. It was just, again, launched a couple of weeks ago. Planet's been able to talk to it, but it'll be, probably a few months in commissioning because it's the first of its kind. Okay, that's about that. Just another kind of personal story that I told a few of you this morning is that when I first started as an undergraduate at university, I had come in and I'd discovered that there was this physics series that you had to go interview for. There was the regular physics, the physics for the non-science and engineering people, kind of like, physics with almost no math. And then there was the kind of normal physics with some calculus. And then there was this other one that was the intensive general physics series. And you had to go talk to some professors to get in it. So I ended up in that program, which turned out to be taught by 3 particle physicists. And there were 6 students. And what was revealed as we went on was that they were interested in how do you create physicists that were actually working. So it was taught with full rigor, looking at every case where what's the next exception you ran into historically, and then what was the solution for that. And I really enjoyed doing that. And in the summertime, I worked as a research technician building these multi-wire proportional chamber detectors that were headed for Brookhaven. So that was as an undergraduate doing that. And in one sense, it's really great fun to come like a full circle back around here. And here we are at this place dedicated to physics and all of the engineering and science that goes behind making it all happen. Great, thank you. Why this talk? I talked a little bit about this, mostly because Ralph had asked me. I was coming, and then Ralph said, "Hey, will you talk?" And I said, "Sure." And then I don't know that there's anything else I want to say about it, except that we are really at a transition time right now with the introduction of the 4.0 release. This will only have been like the fourth time we've made a really large change in the architecture of GNU Radio, in the way where it is like change. We're willing to make, quote, breaking changes, like that, and we've only done that. This will be the fourth thing in 24 years. So I think this is, in one sense, one of those possibly, dangerous and exciting times for us all. And then I want to just set a bit of context for this next part, because all of a sudden the next slide you're going to go, what? So I want to just kind of set up that this was like about 1993. And I had been working for a classic Silicon Valley startup. I was working 90 hours a week. It was a software startup. It was back in the day when there were all kinds of like processors and all kinds of operating systems. It wasn't just that there's like 3 kinds of processors and 3 kinds of things. There were like all kinds of stuff going on. And my then, at the time, girlfriend was super happy. I was completely occupied because at 90 hours a week, how much trouble can you get in? And at some point she was like, how won't you come move into the wine country with me where she lived, right? And so she's says, come, it'll be great. You'll love it. You won't have to work 90 hours a week. And I said, okay, great, let's do that. And at the time then I was thinking about, well, now what? Now that I'm like released from, like intense focus. And I was curious about really what was the nature of like, what is the physiological basis of knowing? Like, where does knowing happen? Does it, where does it happen about it? But what I noticed is I also was unable to pronounce the words in the primary, the abstracts of the primary literature in neuroscience. I said, I should probably go back to school and take like some organic chemistry, molecular biology. Ran into a really great professor who was his last year teaching, and he's like, oh yeah, you gotta learn virology because that'll let you get past the brain, into the brain, and just super interesting. And I was about a year into that, and then this happened. So 1993, the NSA introduces this thing called the Clipper chip. This was this idea that they were gonna build this thing, and it was specifically designed to secure data and voice, and it had this funny feature which was called, it talked a protocol that had this field in the protocol that was the law enforcement exploitation field. So basically it arranged that in every conversation that you had, it made sure that the keys to the conversation were transmitted right up front so that authorized people could intercept your conversation. Now this created quite a stir. It was really a time of really great concern in the U.S. in particular, and I think it was in other parts of the world also. And it was a question about, well, do I have the right to have a private conversation? I looked at it like, well, in the old days, if I wanted to have a private conversation, you and I would take a look around and we'd go for a walk in the woods. It was a completely natural thing to do. So anyway, this came out. And at the same time, AT&T introduces this gadget. This is like a telephone encryptor thing. Does this thing point or no? Anyway, it went in the handset cord. This is like a wired phone. Remember those back in the day? So it went in the handset cord between the things. So it would work with a PBX or your home phone. ISDN was not really a thing in America. It was a little bit later, kind of an interim technology. Mostly people use it for access to the internet. And so there was all kinds of conversation around this. And this is a model, this 3600E, that featured that Wi-Fi. Ah, great. Okay, yeah. So anyway, it handset cord, goes in there to the phone. And then what it turned out was that a year before, they had built the same model that didn't have the Clipper chip in it, and it just had the data encryption standard, the 56-bit key. And it turns out that the order that things happened was that the place with the version with the 56-bit DES encryption came out, and then apparently AT&T went, or NSA went, woo, and so they, in a big hurry, built that Clipper chip then. And then they recalled all of the previous versions of these, and then they introduced this one. So I looked at that and kind of like, well, how hard could it be to build one that doesn't have that flaw? So, I mean, you look at what's inside of this, communication privacy device, and there's like a modem in there because it talks over the phone line. And there's some kind of crypto of some kind, and there's a vocoder in there. And being a perpetual optimist, I'm really in the, well, really, like, how hard could it be? I'm like, a background, and I knew something about, DSP, but so anyway, I headed out to go figure out how to build one of these things. And then I was looking for, well, who else might be interested in this topic? And that took me to this group of people, which were like the cypherpunks. And so this picture was from Wired Magazine's cover for their second edition ever. This guy here is Tim May. He's a physicist from Intel. And basically, he was famous at Intel for solving this problem with alpha particles that were causing bit errors in their DRAM. And what he figured out was that they were in ceramic packages. Your ceramic package is slightly radioactive, and it is corrupting your DRAM. So they figured out how they go plastic packages and more charge in the cells. He went on and won some IEEE award for that work because it was really kind of a mystery at the time. This guy's Eric Hughes. He was a mathematician. And then this is John Gilmore. And Gilmore, I'll talk about in a little more detail because he actually feeds in directly into the origins of GNU Radio. So this is Gilmore. I met him at these meetings. And part of the thing was Gilmore, to a little background, I mean, you can read it, but basically he was employee number 5 at Sun Microsystems. Then he founded a thing called Cygnus Solutions. And Cygnus Solutions was in the business of supporting like the free software tool, like the GCC, the tool chains. And how they made their money was at the time, again, this is an era when there's more than 3 kinds of processors. So a lot of embedded processors were coming out, and the people that were trying to sell those or build things needed tool chains, and they also wanted them early with the simulators. For example, if you got some new game machine of some kind, and you're not sure when it goes, you really want your software developers to get going as quickly as possible. So anyway, Gilmore was part of the crew that did that at Cygnus. And we met, these meetings were happening at Cygnus, which was in Mountain View, California at the time. And there was just a really interesting group of people, and I'll just talk about that. And there's lots of things came out of that group, including some things like BitTorrent came out of there. Bram Cohen would like not shut up. He was always talking about this, always talking about this, always talking about this thing. And people are like, and then finally, like, oh my God, it's the vast majority of the data transfer on the internet. And then John also is the founder of the Electronic Frontier Foundation, which for those of you who may not know, is kind of like a civil liberties group really for the online universe. And they've grown from a small place where there was 3 founders to the place that's huge right now. They do all kinds of interesting things. All right. So I learned some things, a bunch of stuff building the wired telephone encryptors. And the first thing I want to point out is that I did them wired because it was really the only option at the time. There were cell phones, but there was no smartphones. So the choice is like, okay, how can I get any software into these things? There's really no really easy way to do it. So we started out with, what can you do? I can do wired. And in my case, I did starting with what we would call in the US as POTS, plain old telephone service. That's the 4 wires coming out of your wall. And I plugged it in, and I had met, one of the people that I met was Whit Diffie. And Diffie and Hellman were the inventors of public key cryptography, at least in the open. And Whit, his motivation for inventing that is he didn't want to have to trust anybody, including his IT people. So, how do you build this thing out so that that was what was his kind of driving his interest in all this. So he basically became a mentor to me. And so I learned a lot, and a customer. So he was at Sun Microsystems at the time. He was originally a fellow at Sun Labs, then he ended up at the chief security officer. Again, just more interesting people. The point being, I built 2 generations of these. even though I had customers at the very beginning. What it turns out is that I probably had the only customers. And it turns out that it was really kind of one of those ideas where I wanted these things to exist. I wanted to be able to have a private conversation anywhere in the world. But for the most part, people do not care. And I would say, meanwhile, 20 some odd years, almost 30 years later, it's pretty much the same situation. You know, there were some European colleagues of mine that started the GSMK, the crypto phone. There's kind of the same situation. They might still be around. It's kind of like effectively a zombie kind of a business. It never really took off. But I learned a lot and met interesting people. Not the least of which was the classic. Everybody learns this is just because I want it doesn't mean it's a good business idea. But when you started looking at what's in there, towards the end of this run, says what I really wanted was the ability to have like this gadget in my pocket that I could talk on. And I was looking at reading the standards for the U.S. digital cellular standards. We did eventually get the GSM, but before we got there, we had these two. And the IS-136 was partly ran on the same band plan as our original analog stuff. And what was interesting about this standard is that it had, if you're building a cryptographic system, generally the idea is you take your data and you compress all the redundancy down with it, like compression, and then you apply your cryptographic algorithm on top of that. For some particular reason, it was backwards on this thing, which is like the forward error correction was on the wrong side of the crypto. And it was like, oh, wow, how did that happen? Okay, and then we're like, And then on IS-95, this was a CDMA1 system. It had, again, this is like, you could just read the specs, and if you got some clues, you can figure this stuff out. So it had what it was effectively linear crypto. That was not actually crypto at all. There are 42 equations and 42 unknowns in Z sub 2. So there's like 42 bits you got to find, which seems kind of large, except it's linear. And it was helped out in there's a variable rate vocoder. So you're either talking at full speed and it's using, like 8 times as much data, or you're at half speed or a quarter speed or an eighth speed. And of course, at eighth speed, it's like just a few bits being transmitted. However, it's got discontinuous transmission, which means that every time you stop talking or pause, pretty much the last thing you say is nothing, right? And then the thing shuts off. So you effectively have you have this known plain text. So you can just get, within about an eighth of a second, you can solve for this thing. And there was a paper published about the attack. I didn't make it up, but I'm sorry, I looked for it. In 5 minutes, I couldn't find it. But I was like, well, that's interesting. And I just kind of wondered, because here I am, I'm really kind of pretty much given up on trying to do anything about building gadgets in this area. But I was like interested in this. So my question was then like, well, I want to pull the bits out of the air just kind of to make a point about it, right? Well, and I could have been like a regular sane person and just gone and rented a piece of test equipment and just hooked it up, go pull the bits out and be done with it. But I was thinking, well, what's the fun in that? So why don't we try, what now? So as I'm unwinding from that and I'm looking and I'm like thinking, wow, here's my next idea. I'll teach myself digital comms. This is a thing I don't know, looks really interesting. And my wife is she's been super supportive our whole time together. We're about like 30 some odd years together. And she was like, that's really great. I'm all for supporting that, but please, I don't want to be poor while you're doing that. And I'm like, okay, I hear you. Good. And I started looking for, well, what do I need? I need like a development platform. I want to go out and buy something where I can start to teach myself this stuff. So I look around and I'm like snooping around on the internet and I find this basically eval board that's from this Canadian company. And it had like an RF front end on it and an FPGA and a DSP and some other kind of processor. And it was like, wow, it has like everything. And it was about $10,000 US. And that was kind of in the realm of my personal, I would spend that much money to get a new thing I'm going to go teach myself something on. And then I go look for like the software licenses it was going to take to turn all this on. And that was like $70,000 of the software licenses. And I was like, whoa. Not doing that. So I was kind of like, So then, meanwhile, life goes on. I'm kind of looking around, but I'm like, okay, I'm still interested in this. And then I've been in contact with Gilmore, because he and I have been in contact for over the years. This is meanwhile like 7 years from when I first met him. But we kind of talk every now and then, a couple times a year at least. So I'm like, go up to San Francisco. We have a nice dinner at this Thai restaurant. We're just sharing about what's going on. I said, hey, I'm looking at trying to teach myself digital comms. There was this standards are kind of messed up. And but I said that this license, it took like $70,000 worth of licenses. Then he goes, Gilmore, again, having made money, building and free software, licensed under the GPL, says, well, let's start a free software project. And he said, and I said, okay, great. And he says, well, make me a proposal for funding. And I was like, okay. So, I talked to him like one more time. And what's good about, the thing I want to keep pointing to is about relationships through all of this. And I think it's how the whole world works. But in particular, here's another example. Gilmore had been a customer. He knew me. He knew what I was capable of. And he was like, okay, I will fund this thing. We found a donor-directed charity, and he basically agreed to fund the development of what became GNU Radio. And part of my very favorite part of it was that it was really easy. It was some of my favorite time to do work, partly because the arrangement with John is like one phone call a month kept the money coming. And I was getting paid a reasonable rate. And I didn't have to keep track of any hours or things. Just go do work on the thing and, keep me posted. So that's how it started. But then we return to the question, okay, well, where do we start? Now we're back to where do we start again? And on this time, it's like, so I start with, I graduated with a degree in electrical engineering, but I was really mostly kind of on the computer science side. I'd kind of gone to the dark side from the physicist point of view, because they were like, don't get sucked into those things. They're really interesting, And I was like, sorry, I did, And so, but I built a kit out of, could have done some amateur radio thing, but this was like a company like Ramsey Electronics. It had like 14 transistors in it. So the point being, there's no magic in there. It was all like on this board. And then you get to learn how to probe, RF and not disturb the signal while you're poking at it, right? Kind of useful. I figured before I try to build ones that like almost completely abstract and out of software, I probably ought to know how to build a piece of the classic hardware. And we started out then to look for, well, what's the starting point? Somebody else must have looked at this. There was some earlier, there was a military project called Speakeasy that Joe Mottola had done. There were some papers published about it, not really directly applicable to what we were interested in. But then I was snooping around and I came across the MIT Spectrumware project. This was a pretty interesting thing. These two URLs, they're captures of different times. The thing is effectively, well, there's a lot of dead links back in here, but they published 14 papers that are really quite irrelevant. They discovered a bunch of stuff that was useful about ways you would do computation if you were going to do it on a general purpose processor, as opposed to it was all like one DSP. It was always like one sample in, one sample latency all the way through the things. And they also figured out some algorithms that were handy to do on general purpose processors. And there's a whole crew of people, including Venu Bose and some other people. Tenenhouse is one of the professors. He had then gone to Intel, and I went and tracked him down just to go visit and say, hey, tell me, how did it go? Anything, I'm looking at doing something like this, anything you can share with me. And he was, as helpful as he could be. Anyway, they had a code base, and it was a reasonable place to start. I think about 5 or 6 people received PhDs working on this project, and it was around this particular code base that they were using. And that's where it originally came from. That's dead. I don't have the whole code base anymore for this. P-Spectra is what it was called. It was in C++. I have no idea what the P of P-Spectra was for. And then along with that, they had the same problem everybody has when they get here. It's like, I want to do a software-defined radio. So I somehow need a way to get from the antenna into the computer. So at a simplest case, you need some kind of way to get, high-speed A to Ds and D to As connected into your computer. Now, at this time, so the fastest things we had going that was affordable was PCI, not PCI Express. So this is the PCs of this time. They built this board they called Guppy, which was basically as simple as you could get, and it just had some, SMA connectors on the end, and then you plugged in whatever you wanted. Ralph, I know you had asked at one point, or I saw it in the comment in the code about where did this double buffering idea with the memory double mapping the same physical memory into two places in the virtual address space. It came in the Guppy driver. Spectrumware itself didn't do it. They had one paper, but it didn't really talk too much about it. But I looked at the driver to see how it worked, and I go, wow, that is super clever. So there was a trick used in GNU Radio now, since the beginning of time, where to avoid having to manually manage a for loop, if you're like computing like some FIR filter, and you want to not have to figure out, am I at the end where I now need to wrap? So what you can do with pretty much all contemporary machines, the machines that it doesn't work on are ones which have virtual mapped caches, which don't exist anymore. The HPPA was an example of that. But you can do this trick where you have a piece of virtual memory, and then by using the right operating system calls, you can basically get it to map that same physical memory into the adjacent piece of the virtual address. So basically you have this sequence of data, and then it repeats right here. So what happens is you can just compute straight across that boundary, and your software doesn't have to know there's a boundary there. It turns out to be super handy. Anyway, that's where it came from. That's where the idea came from. All right, and then this was the very beginning. So we started with a P Spectra, and I was going to start to clean it up. And the very first thing, this is the first commit. It was 2001. And the first thing happens is there's a return value off by a factor of 2, and there's a stir length related buffer overrun. So this is how we get started with P Spectra, which I would, with no offense to any former or current graduate students, I would call, grad student wear. Like it got the job done for what it was supposed to do. Yay, we learned, we got our degrees, we went on, and they left it for other people like, me to come across. So we started with that and then went to town. Okay, Moore's Law, of course, obligatory. This is mostly why this is in here is just to set the stage for what's the resource availability of this time. So let's assume it's like 2000, it was like 2001, and that puts us, here, and then to say to 2010. And this thing is, we are in a really great time. This is the Moore's Law straight transistor count area here, all right? And then it kind of flattens out up in here. But what also was happening in this period of time as the clock rates were just getting faster at the same rate. You did not have to do anything but wait, and everything ran faster, which was really good news because if you think about it, we were trying to do these computations on this general purpose processor. And if you get the data rate up high enough, you cannot compute it in real time. So, but part of it is we could see that, this trend is really working for me over here. I could build it, I can test it, I can run it. In some places, I can capture signals that I can go in on demod or whatever, but I can't do it in real time today, but I can do it in real time in 2 years. It was a very interesting time. And then part of what you see where it flattens out, all of a sudden you start having, here's 8-core systems, 12-core systems, 61-core systems. And we're now back into this realm that we have now, which is they're not getting any faster. The Dennard scaling has flattened out also. We've got it, we're power limited. The only hope at this point architecturally is more processing. And then of course the things that people are doing now is other architectures for computing. So there's the whole GPU thing and making all this heyday in AI, but it really isn't the right architecture for computing those things. It just happened to be the one that was at hand. And there are other people who have designed graph processing machines. A guy that used to work at Intel and at AMD as a CPU architect. I saw him do a talk on this. Here's how it would go if you were actually you're trying to take that graph and run it. This is what the hardware you would build. So anywho, that's kind of the environment that we have. And we're again stuck out here in a place where we're being forced into heterogeneous systems. We've always pretty much needed some kind of FPGA or something for the very bottom of it. And I know that pretty much, so I was talking to a gentleman back here about trying to do the RF, the high performance RF at the very bottom is like for my control system, it's got some exact sample by sample and it's an FPGA, and those things are a pain to program. So, all right, and I wanted to start at Matt Edis, who recently, a couple weeks ago, was elevated to IEEE Fellow for his work supporting software-defined radio, which is pretty exciting. Matt was, he was started at the very beginning of GNU Radio, and because one of the things we looked at was, hey, what hardware are we going to run this on? And we found some things which I'll talk about that were let us get started initially, but like just the data acquisition board was costing more than the computer that we were going to run it on. So anyway, Matt and I, we met. We started, he had a job designing like Bluetooth ASICs that were used for some things. So he had a background in signal processing, and my background was kind of like generally like software. Yeah, I can do that. And I'm curious. So those are the things I got going for me. Anyway, he and I used to get together on the weekends and go, okay, I'll come to your house and, you know, we'll work in your home office. And then eventually he gets a bigger office and so on, and, you know, like that. The initial hardware we used, again, we had the same problem with the MIT people. Somehow I got to get samples into my computer. And again, I had one Guppy board. They sent me one. I sent them. It was funny. I was looking and it had, you know, do not dispose of this box. It was one of those nice kind of folded cardboard with the foam on the inside. And it says, you know, don't dispose of this box, reuse it. And I realized it's still, meanwhile, like 25 years later, it's still in my line of sight when I'm in my garage. It's got something else in it than the Guppy board, but, you know, it's like still there. Hang on, go in the right direction. Matt, okay. And this 4020 board, we ran it at 20 megasamples single channel because that was all it could do 4 channels, but it couldn't do them at 20 megasamples. And that was a straight just bandwidth limitation of the PCI bus. And then again, it was just expensive. The thing was like at least 50% more than the cost of the PC we were running it on. And then we had the question of, well, what's our RF front end? And it turns out we found these cable modem tuner eval boxes. So if you look inside your cable modem, there's a little like, you know, metal can in there that had, at least in the US, it has like an F connector on one side and, you know, something out the other side. So we found those. That was reasonable for us. We originally used some US-based ones that were set up for, we have 6 megahertz channel spacing, and later we switched to European ones, which had an 8 megahertz spacing. And that got us to go, but again, this thing was not cheap. There were also, when we were looking at hardware, we looked at some, well, if you really wanted to spend some money, there were lots of people that would sell you fancier hardware. You know, but it was like in the, you know, 20 to 50 grand kind of a category. So that was not, we started the thinking about what do we want? You know, what would we want if we could have anything we wanted? What would the interface be? And that was a conversation that evolved over time. It was happening at the same time that I was mostly working on the software, but working with Matt on the development of what became the USERPs. And then when we started out, well, what are we going to build? What's the first thing after you what's the hello world of software-defined radio? Well, we thought, let's do like broadcast broadcast FM. This is your regular wideband FM, and you get in the car, right? Before there was digital sideband on it. And it exercises a fair amount of things because we were going to bring in kind of either almost the entire band with the other thing, we can't get the entire band, but we could get like half of the FM band. And then you have this question of like, well, how do I do my channel selection and decimation and how I do that efficiently in software? There's the FMD mod itself, the signal processing involved in that. And then there's like audio output, but you've got, oh, your PC does audio output, no big deal. But then you run into this problem, which is, I would call it the 2 clock problem. And this is still not solved generally. And I don't think it's currently solved in the code base generally. And it's a real, like, it's the kind of thing you want to solve. And this 2 clock problem is, you know, I got a clock that's my A to D converters and D to A's are running on, which is almost certainly not shared with the same clock that's running my audio in and output, the A to Ds and D to As on this. You find the problem in other domains. Also, anytime you have like two different radio systems and there's sample rates are different between them, or one is remote, one is in orbit and one is on the ground, and there's a bunch of Doppler happening also. And what you also want is you want really low latency. So you really want the system to basically make like fudge it on like a per sample basis. Like on the audio, you can get away with, if you're careful, you can either insert or delete one sample and keep the timing continuing to match, even though it's off by like a part in 1,000 or something like that. If you don't, what happens is you end up with a thing that just gets a larger and larger and larger delay in it, which is terrible. Or the other case, and then you underrun because you're not keeping up. So again, this is something with the GNU Radio 4.0 scheduler, real time, yay, we should make sure that we've got a story that's about solving this problem. Okay, we got that working, no problem. That's then what happened is like we need the next more complicated thing, and in the US, you got some funny standards. I mean, I look at the European standards for digital, terrestrial digital television, and wow, it really makes great sense. We had this thing called the Advanced Television something, ATSC. And it's a reasonably complicated waveform, which means it kind of has one of everything with regard to signal processing. It has like a block-based forward error correction in it. It has a convolutional error correction in it. And it has, kind of a bunch of things. So it was a really good thing to try to build. And there was no way at the time we were writing it that we could run it in real time. But they didn't stop us from being able to collect samples in real time. And I remember my office in Monterey, I got a big outdoor antenna and had it in my office and pointed towards the first television station that was broadcasting in my neighborhood. And we could just collect samples and then go grind on them. And then while we were doing this, and Gilmore had suggested this, he's again with his EFF hat on, because there was a group called the Motion Picture MPAA, Motion Picture blah, 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 something, who are the people that were they were the kind of people that were trying to make sure your set-top box couldn't play anything back initially. And then they wanted on this, they really wanted to, without going too deep into it, the television stations in the US do not pay for bandwidth. They were grandfathered in. So they might pay some kind of fee, but the fee is on the order of a few $100s, as opposed to the cellular carriers who have to pay billions of dollars for access to spectrum. So there's that as the background. And then the Motion Picture Association of America and their copy protection technology working group made this proposal that they were going to use this thing and transmit this new digital signal. And they wanted to make sure, they wanted a bit in the data stream that said, "Thou shalt not copy." And we were like, "Oh, okay, really?" And they were sure that if they didn't implement this bit, that people would be dying, industry would, it would all be terrible. It would be terrible, terrible, terrible. So, but we wanted to, what they had proposed for us to do is build this ATSC thing. We'll basically, I said, yeah, we'll put the code in there that says if, the broadcast flag, which is one flag set in the header, is there, then we won't copy. But we also made the point that this is free software, and the very first thing anybody's going to do is just like if 0 and remove that one line that checks this bit. We also had prior art and court rulings that were related to crypto, where it was basically ruled that in the US, that source code is protected under the First Amendment. It is an expression that is protected, and so we have this open source thing that this battle got fought kind of in the crypto area. And then we're like, oh, we'll apply it here. We've developed this, software gadget that will receive this thing. And then, yeah, I can even put the flag in there to check the flag. Then, don't save it to the disk. Anyhow, we built that, went to this big, conference down in Los Angeles where the big Hollywood producers and the were there, and there was like, okay, here's their head technology guy, head lawyer, and then here's like the, the different people building consumer electronics, and they're all doing their thing. So we go, and I go under the, the EFF lawyers, and we just tell them what we're going to do. We're going to build this thing, and we say, okay, we could put the bid in. People will take it right out. It turned out that argument wasn't enough to get it killed, but that the EFF went on and killed it with the American Library Association, basically challenged it a different way. And so that bit never got deployed, so people are free to, look at the bits on the air and do whatever they want with them. Anywho, I guess what I want to say about this is I noticed that having this as a target to build, which was a fairly sophisticated waveform, was super useful to give something like, it's like your test, it's your use case. And we built the transmitter and the receiver kind of from the bottom up, the outer edge first that you could connect together, and then built up both sides, the transmitter and the receiver in parallel. Super handy. So I would think whatever we're looking for with GNU Radio 4.0 cases, on the radio side, we should pick some interesting things we want to do. And I know that some of us have already had conversations about this, but let's make sure we're building something that's interesting and hopefully useful for somebody, or lots of somebodies. GNU Radio 0.9 was the very first. This is a little bit scattershot on ordering here, but there's a whole bunch of stuff going on in parallel. This was the very first public release. This was at the end of, I started with the P-Spectra code. And by the time we got done, like bug fixing and restructuring and modern build system and all that, we ended up with about roughly like 30% was P-Spectra code and 70% was new code. And the total time, and in the meanwhile, we'd done drivers for those boards, and there's a bunch of work getting done. And it ended up being about 2 years to get this all done. And at that point, we were saying that's the end of that line of development. We'd learned a lot. There was not a real future for us. I could see at that point that there was better options from like a software architecture. And so we parked this, and that was, that's what happened to that. Again, this is all kind of happening in parallel. So back to the question of, well, we've been buying these measurement computing boards, but they're very expensive and they require a desktop kind of a thing. And I'm pretty sure that Matt and I were having some conversation around this starting around in 2000. And I saw that the first commit I did on the software for the firmware was in 2003 in July. But I do remember we were just trying to start with like kind of what do we want? What do we want? What do we want the price to be? We talked to some folks that were doing that had built stuff, and they suggested USB, and there was USB 2 at that era. And they were already mentioning there was USB 3. Now you think like USB 3 is like 15 years down the road from when we were having this conversation. But anyway, we talked to people that it was kind of like, okay, well, it'll be USB. There was a part that, was the FX2. The FX2 was like had a parallel interface on one side and talked USB on the other side. And that was, this whole idea was what started with the usurps. And we used the cable tuner, the same RF front end we had before, which was this eval board for these cable modems. All right, any questions so far about anything? Okay, I'm going to talk in a little bit about kind of some funding things, like how do we get paid? I mean, I worked, like it turns out I worked like 2 years on the first thing, and then this thing took another 7 months. This was the next version of GNU Radio. There was no 1.0, there was just 0.9, and then we started to yeah, you're welcome. I haven't seen there's any shortage of integers, so I think we were okay. It was just like, it was never going to get to 1. So we started off, so the 2, and there was no, don't ask me, there was no 2.1 or there was 2.2. This was one which is really a rewrite. So we reused, the algorithms were reused with regard to the signal processing blocks. But I had learned a whole bunch from trying to working my way through the P-Spectra code, and we saw that there was looked like a better future to build out. So this includes really the kind of stuff that we still have in there, the streaming part. This was the idea that you had the the buffering where you had the single writer, multi-reader things, and the flow graph, and all this whole business was in there. And it all had the Python bindings in there. And in fact, in the 2.2 series, the 2.0 series, the high-level manipulation of the flow graph was in Python, because it never was critical performance. Once you got that graph described, we would just flatten it all out, and then you handed it to the C++ code, which I thought was like really great. And then we had some customers that wanted to be able to deploy with no Python. So that got addressed later, but you know, we live and learn. So anyway, and I also just like to say, this is one of those ones where I was fortunate enough to have funding of being the people that like trusted me, you know, and to say, you want to do what? You want to start over? You know, and yeah, I do, because it's going to be better for the future. And it, you know, we got it done in much less time, and it was the right call. We really had something that has now been carried on for 23 years. Not that it hasn't been improved along the way, but this fundamental architecture on the streaming side is the same core principles. All right, now into funding. So this is related into some conversations that people have asked. Ralph and I had conversations around this, just about like, well, how do you grow a project and have it go for 20 some odd years? And there are a lot of, there's a whole lot of, software projects that get started and they go for a little while and then they die. There's a relatively small handful of them that really, I don't know what the percentages is, but it's like low till you get something that it can go 20 years. But I know that part of it is there's people getting paid to work on it. They're getting paid one way or another. I was fortunate enough that I was just working on this full-time on the core and the design of it. There were other people that were working either for some company or enterprise or whatever that was related. So there was again, people that were either part-time or full-time that were working on it and letting us, evolving it and letting us know what happened. So there's this idea that it's all free. I mean, no, because you can't get good talent to really work for free for a long time. You can get free talent to work for, for maybe a couple of weeks because it's cool. But, if you want it really full time, you need funding. So I was fortunate enough that I had Gilmore fund the original development, which ended up being roughly, I don't know, a couple of years. And then he had introduced me to Jay LaPro, who's a professor at the University of Utah, who was running this place called, he was the head of the Flux Computing Operating System Research Group. And they although Jay died in 2008, his group carries on and they have this big test bed called Emulab that is available to pretty much any, academic kind of person. And it was designed for, it was early cases of software configurable networking and delay and all this whole thing. And it was a big, expensive thing. And Jay was interested in the thing we were doing, and his whole group were kind of, in one sense, the masters of writing grants because they'd been doing it for years and years, and they had, a machine in place to do this. And he was like, "Great, yeah, well, you guys write your part, and we'll get it all worked in there." And he was, when we first got funded, he was like, "Wow, this is the first time we've ever been funded for for a proposal that was pretty much just all bullet points." And we were like, "Oh, it worked." So anyway, that was the first experience for me of National Science Foundation funding. And it basically funded Matt and I to work on another couple of years worth of things. So part of the early development of the USERP was covered by this. And what the National Science Foundation really wanted for it, what the thing that was about was their customer are academics, right? So there's lots of students. We wanted to basically serve as people that were wanting to learn about digital comms and build stuff. Because although, hey, MATLAB is super popular, but do you ever have heard of anybody that actually deployed a radio built in MATLAB? So there's this whole question about, there was a famous paper by Fred Harris that starts with, let's assume the system is synchronized, right? Which is the hardest part of the whole problem that mostly gets punted. And your MATLAB workbooks don't have the solution to that in there. So anywho, there's National Science Foundation. That was really good. We worked through University of Utah for a couple of years, couple of funding cycles. And then also at the same time had got a group from Rutgers who run this place called WinLab. This is still happening at WinLab. They have a big indoor test bed, indoor and outdoor radio test bed called Orbit, which I don't remember what it stands for, but it's a big building. The Orbit building is probably, I don't know, it's like at least 3 times the size of this room. And it's got all these radio nodes hanging from the ceiling and all kinds of equipment in there, including even today on, I checked before I came, there's like still usurps in there, and there's big usurps and small usurps. And so they were actively doing that research. So I think there's more. If we had people who were interested in this, I think there's money that could pay for developers if they want to go work with those guys and produce something that they're interested in, and we could feed it back. So I also ran, for me, I ran later into, through BBN, had a DARPA-funded thing that they wanted my help on. That was also a nice way to receive money, because again, it was simple. It was like, here's 1,000 hours, for the year, do 1,000 hours in a year, and here's what you want to do. And it was like really, with regard to low friction about getting money, not a whole lot of paperwork once you've got it set up. So anyway, and then there's like, on and on and on. So the point being that there are ways, and Ralph and I and some others have started talking about, well, how do we fund this? And how do you fund it in the European context? What you do for different organizations. Like, how do you fund something that you want to exist? I mean, we've got the example right here of FAIR, which is like, whoa, what, 3 billion euros or something. So, and I think one thing I see is that there's definitely people that want it to exist, right? There's like, they can tell a story that is really like, yeah, we want it to exist, and it's going to make it better for people, not just us or researchy people, right? They're going to like, no, you're going to have your, medical application or whatever else. We'll understand stars. And so there's like, how do you sell that idea? And I say that in the kindest and gentlest mean of enrollment or speaking and having people be enthusiastic about whatever it is that you're after. Okay, that's the story on funding. Again, there's a pattern here I think that we can repeat. It's not, But the point being, really nice to have money to pay for developers. And I know that at some point we can, yay! And we don't want it all coming from one place. We want lots of people involved and then, pitching in. So anyway, I do think there's ideas. I think there's like conversations to be had, but it also just takes people to be like in relationship with people, calling and seeing. And particularly, I'm not sure right now, again, I've been really away for about 14 years. I've been kind of keeping an eye on the project, in one sense, the way one would keep an eye on their adult children, which is like, it seems like they're doing all right, and so I'm like, I don't know all the details, but I don't know, for example, how well are we doing in the academic community, right now? Are we the number one choice when people are like working on the digital comms and they're working on a PhD? Are we the tool they use? And if, I don't know, but if not, what are they using and why not? What's missing? Is it too hard to use? Or is it, whatever, like that. So, okay, community building. This is another part of it. One thing that made the whole thing go. So one of the things when we started it as under the flag of the Free Software Foundation, they provided a bunch of infrastructure, which included, we'll announce your project to our big mailing list, right, to the general mailing list. But then they had, they'd build you a mailing list, and they had suggestions for how you ought to do this, thing, because we've done it for a long time, how you ought to manage your code and how you ought to make releases, and they ought to be like this. And there's like a bunch of stuff that is, in one sense, great, and how you want to, what's your build system? And they were like, try it this way, because we've had a whole lot of experience. And again, part of it went back to an era that was before there's only 3 processors, and 3 operating systems. So some of that stuff, if any of you have been around the AutoConf universe and went, oh my God, it solves all kinds of problems that the modern things that most people use today, like CMake or something, do not even begin to touch. Like if you ever try to compile for the host and come and cross-compile in the same build, it's like impossible to CMake. It's a total pain. Where AutoConf and AutoMake, it's all that, it just works great. So anyway, that's my pitch for that. There's not to say that there aren't other options that have come, but let's not forget the stuff that did work. Now, on the specific part of community building, I'm, as a much younger person, I was not so much of a kind of happy, loving people person as I am now. I was mostly about, why are those people talking about the weather? You know, as I'm a kid and you're looking at your parents and their friends talking, you know, it's kind of like that. I like things, you know, and then eventually I just discovered I like humans. And part of it was with NSF funding. Part of it was like, okay, you're getting this money from supporting science and academics. So I turned out that one of the things I ended up doing was making sure that anybody who was using it had support. And at one point for a couple of years, I was personally responsible for 20% of the traffic on our GNU Radio Discuss mailing list. Yeah. Yeah. And it was good. I mean, I preferred the mailing list as a way to survive because at least it was archived. You could point people to it. I know you guys are really like on loving the chat, the you know, the matrix, but it's not as indexable or searchable later, right? Anyway, so there's about that and again, it was like answering questions, being helpful. The other thing was about going to the, you know, the PI conferences for the particular department of NSF. Those were really fun. And first of all, you meet all kinds of people that are doing really cool stuff. And I was at one that was really surprising because people had known, and it was a part of NSF that was called CISE, which is where our funding came from, both places. And I was at this one conference, and there was the other PI stood up and said, "Give Eric the money." They were like so happy for what we were doing. I was like, "Wow, that's pretty funny." Anyway. But community building, it's like talking to people. I mean, like talking to people. How are they? What are they doing? How are they? You know, even if it's like you know, you guys here at GSI and FAIR were never on my list of the likely users of GNU Radio. And then I like find out indirectly that, oh my God, you've been using it to like run some particle accelerator? How does that work? So there's that whole part. And then now I'm here because I'm curious. And, you know, besides, I think it's really cool. I like big, complicated, you know, expensive engineering things and science and physics, all that good fun stuff. So there's a part, and I think this doesn't happen just like one person. It's about, you know, there's some basic stuff that goes beyond like the checklist that everybody gives you. It's about really like caring about people and talking to them and what are they in and encouraging and finding out what would you like, what do you want to do or what's your crazy idea? And then answering questions. And then part of it is trying to build out infrastructure so you don't have to keep answering the same question over and over and over again. Because otherwise it's really kind of tough. But that's what I have to say about. Any questions about this? I think this was crucial to the success, actually. Because otherwise, I mean, you know, you can't just sit in your garage or whatever and do this and not talk to anybody and expect to end up with a thing with users. All right, now remember, this is not television, so if you got questions, you can, you know, raise your hand, we'll get you a mic. Yay! yeah, okay, great. I mean, you wanted to, yeah? Okay. You're just stretching, okay. But really, like I said, I'm totally willing to, I once, as a side note, I once spoke at a place called the Vanguard Technology Transfer Institute, which is kind of like C-suite kind of people, CTO, CIO kind of folks. And the way that they ran their events is that if you were a speaker, you got a 10-minute head start. And then everybody in the audience has like a push-to-talk mic. And the rule is they give you 10-minute head start on your like 60-minute window, and then they can just butt in. It was super fun. I mean, it was like, you know, if you like that kind of engagement. Anyway, I'm trying to drum up some here, just a little, but you know, anyhow, let me know. Okay, and there's some acknowledgement. I have more I want to talk to that's more a little bit about the future. And again, on the future stuff, I really do want people here talking, because you know I've got some ideas, but I've been kind of away, all right? But I got my, you know, welcome to the Academy Awards. I got my list of people I want to make sure we call out. Now, some of these are in kind of chronological order, just to kind of, these are people from the beginning of time. So there's Matt, who I spoke to, and then Jonathan Corrigan, who worked with me for a long time. And the thing about Jonathan I really loved was that he knew what production code was. He had worked at Intel. He had, managed the production of, making of production code, which is like well tested. He knew what a customer was, so it was like really good to have that kind of person around. He managed our releases for quite a while. He also kept my head on straight about many things and taught me about how to relate with him and some other people in a way that's, maybe more pleasurable than my possibly like over-the-shoulder unsolicited code review, And he did a lot of work on both the 2 series and 3 series code bases. And then later, after I was gone, he's had a stint where he was serving as the chief architect starting in 2016. So again, it's really, you just can't do this. It's not a stretch of it alone. I mean, I did write most of the original code base, but I did not build it all, and I did not reach the scale by like sitting in my office, The next person I want to say, again, these are kind of chronological, is Tom Rondeau. So I met Tom when he was a graduate student still at Virginia Tech. And I went down, because Virginia Tech has a pretty good community. There's a lot of people coming out of there that know something about digital comms. And he took over. He was my hand-picked successor, basically. We had at that time, had effectively the benevolent dictator for life kind of a role model for leadership, which kind of works out. Somebody's got to make decisions about what goes in the code and what doesn't. Even when you go to another organization, you still, somebody or some buddies have to be saying yes or no, and they may just be saying no, but it needs this, and then it would be okay. Otherwise the thing turns to mush. It just turns into a big mess. And then I also wanted to thank him for his continuing to support to the GNU Radio and GNU Radio community, even after he was long gone leading the project. And then basically we're going to go down to the other people who have kind of headed the group. So there was Ben Hilburn, and he took the lead after Tom. And then he was part of the reorganizing the whole leadership structure, where we're going to retire the benevolent dictator for life, which, yay, go General Assembly, right? Marcus Miller right here for serving as the chief architect starting in like about 2018. Are you still technically that? No. Who is the chief architect? Okay, right. And Derek Kozel, who's not here, but he ran it also, right? Was he the president of for a while, and the co-PI to SETI, which is like, again, when I heard about that, I thought, wow, that's an interesting arrangement. And I did go out and tour the SETI facility and like I had a scheduled, knock on the door and get a tour on the inside. It was really kind of cool. It's a big, it's the Allen Telescope Array. It's up in a really quiet valley in Northern California. It's kind of fun. And Josh, the current president, yay, Josh, yay, Josh. Again, I have to say that it really, my heart goes out to it because there's like a lot of, leadership. It's like, somebody's got to like raise their hand and say yes and kind of, talk to people and make the decisions. And, and it's never just that there's like one person doing it. And then really there's a whole bunch of long timers that have been around GNU Radio, like from when I was here, and some of them are still around. And there's like Martin Braun, not here today, and Phil Ballister, and Mate, who was doing Debian packaging forever and still doing it. And there's more, but there's some people that have been around since I left and then continued. So that's, for me, quite interesting. And then Ralph, and part of in one sense, the new crew of people, the whole FAIR team, the people, oh my God, they're using GNU Radio, something about a particle accelerator. I'm also looking while I'm here to hear more about like, which part of it are you controlling? I mean, I can kind of get event capture or whatever. And what that brings is like, oh my God, so you have like safety critical stuff. Oh yeah, you don't want to break the machine, or, I'm assuming that keeping people from being irradiated is handled by some other things like concrete and like stuff like that. So anyway, and many of you here, I don't know many of you, but I really do want to get to talk to everybody while I'm here for the week. And I've talked to some just random people so far. It's like, what is your interest and how did you get here? What, if you're using GNU Radio, yes or no? Interested, like talking about RF? Okay, good, that's in the territory. And the challenges around like, hey, how do you do real-time control of this really big, accelerator? And it's high power and it's like, sparking against the wall and you're like, not what you want. So that's what I have on that. And I'm sure there's people I missed, but I wanted to just leave you all with sense of like a gratitude that, including those of you who are just here for the first time to go like, well, I just kind of came to find out what it's about. So again, we have the track that is for people. We've got a whole track for those people. Yay, Ralph and team. So, all right. And now looking to the future. This really, I'm not kidding. We want like audience participation here. Okay. Okay. So here, what I've got is a couple ideas or thoughts, but basically we're at a transition stage right now. We have built, again, there's only been a couple, and there was like the 0.9 to 2.0. At that point, there were very few users. It was no big deal. It was definitely an improvement over what we had before. And then there was an evolutionary step from like 2 series to the 3 series. I mean, everything, a bunch of stuff changed, and we made breaking changes, but it was kind of this evolution. We are really at a point where we're proposing big changes, and we want to know, you know, partly we're here together to the week on at least the 4.0 part of the gang to like, are we building something useful? Is this going to work? I'm sure it's going to work for FAIR because you guys are here and it's going to work for you. But is it going to work for the rest of us? That's kind of like, and I don't mean that glibly. It's just kind of like are we building something useful? Okay, so what, anybody got anything to say right off the bat? Okay, I'll get you a better question. So I got some questions that are in this category of who is currently using GNU Radio? What communities are using it? And again, this probably varies depending on what continent you were on. Oh, look at that. Yay. Okay, give that man a microphone.
Someone has to talk, right? So we do have, of course, still academia. We're like the #1 thing where people go to when they need to teach a modular STR approach to students. We do have, obviously, the big kind of research things. Oh, fair. We do have satellite yes. ground stations. We do have air control stuff. We have a lot of automotive people that start to experiment, or long time ago already started to experiment with things like fleet management, right? So we're going more industrial, I guess, in total than we used to. What I think has decreased a bit over time is the number of PhDs that primarily do something on radio, which is simply because the trends, right? SDR was the big OOS thing, right? Mitola and everyone yes. after him basically swam on, and that was obviously great for a free software SDR system. And we're kind of, trying to find a niche there again, right? Some things are really just harder. We're on a PC. Even with GR4, we might not be doing the bandwidths that a modern cellular system does because, well, the channel coder doesn't get any easier.
Yes.
So that is still super interesting. Then, but what we're really good at is the whole fusion thing where we have, well, this is a big 5G, 6G research topic. It's like joint communication and sensing, where people are actually looking into how do we do the communications and also know where the pedestrians are and also know when to brake because there's a car coming around the corner, kind of things. And these things are where, well, you can do that literally like very well in say, MATLAB simulation, but you're going to write a lot of MATLAB code.
Yes.
And nobody likes writing MATLAB code.
Yeah. Great. Thank you. All right. I'm going to give you another question unless anybody got an answer to this or is anything they want to say about it?
Yeah.
Okay.
Maybe we should have softened them up with some more boost in the beginning. Maybe first beer garden and then the discussions.
Yeah. So we're kind of, we got about 4 minutes left here to stay on time, but I'm going to get somebody else to speak here before we're done. But I want to let you know that I'm around this week and I'd love to talk to everybody about whatever your interest is, because I'm kind of that kind of person. All right. This was a question. It sort of got asked and answered already. It was kind of like, who's using it and how are they being incentivized? And you guys might have, I don't know that we need to do this right now from the front of the room, but there is this idea. This is back to how do we get people to do the work? So, there's hobbyists that will do work, and some of those have made contributions to the core of the system. And this one, I think, is one that, well, part of it is if it's teaching, learning, and research, well, research, we're in the right place, right? And then again, these are just kind of questions, and we did kind of talk about this. But this last thing over here is like, who are these PIs or co-PIs that we know? I mean, who's using it now? Like, really, what are their names? Can we go talk to them? And can you go talk to them? I mean, I'm here just in one sense cheering. So, anybody have anything to say about this one? Okay, because partly what I'm like looking to solicit on this is, are there problems that GNU Radio could solve that it's not currently solving? And why? Is it like there's a steep learning curve on it, or not quite right? Or there is definitely any SDR, there is an incredibly steep learning curve, because you got to know about at least enough RF to know that there's not all linear and ideal. And then you got to know some DSP, and then you got to maybe both the theory and the practice, and then comms, the theory and the practice. And then if you're going to do the low level, like new blocks, you got to know how to code. So it's steep, I know. So, and then we've got with things like the GNU Radio Companion is an idea, well, we've got this big block set. So then you still got to figure out how to put the blocks together. And I think it's an area where we've probably got a pretty good start on it, but I think we need more fully worked examples at demonstrating this is our best idea of how to build this kind of radio. Now, I know, Josh, that in the work we were talking about, and with Danny, it looks like that's a perfect example. Is Danny here yet? Oh, yay. All right. Hi. Hi. They mentioned your name when I was at SETI. They said, oh, yeah, he can get his own antenna he can use out there. Yeah, yay. Anyway, that kind of a thing is like figuring all that out. And then, okay, I got 1 minute to go. Anything else I want to say here? Oh, questions, discussion, and just general inquiry. This, I think, is really, a lot of this can just happen during the week when we get together. I care about, again, this question about who could we serve that we're not currently serving and why? And again, is there some stumbling block in the way? Is there something that's too hard or it's too awkward? I know, for example, that with GNU Radio, it's traditionally been very hard to make the transition between like the PHY layer of your radio into the MAC layer. It's kind of traditionally from a streaming-based thing into all of a sudden I have like protocol data units. I got from this to this, and it's how do we architect that such that there's a well-known, straightforward way to do it as opposed to a bunch of different ad hoc solutions. So, okay, that's it. Thank you for your time. Looking forward to speaking to many of you while I'm here for this week. I mean, I didn't just come here just to do this. I'm here to plus get the tour and, see big science on the big scale. So again, thank you very much.